Welcome to the 18th video of the physics lecture series for the National Science and Mathematics Olympiad. In this video, we will apply what we learned so far to describe projectile motion. This motion means that an object is launched at an angle. Following the launch, the only force acting on it is the gravitational force. Thus, the only acceleration we need to take into account is the gravitational acceleration g, which points downward. Describing this motion, we use the fact that the projectile was launched with an initial velocity v at an angle theta with the horizontal direction. In this case, the object will follow a parabolic trajectory. Let's first describe the motion along the x-axis. There is no acceleration in this direction, so we can simply describe it as uniform linear motion. There is a constant horizontal velocity, which is Vx equals Vi times cosine theta. The displacement as a function of time can simply be calculated using the formula for uniform linear motion, so x at a time t is Vx times t, which is simply Vi cosine theta, as we saw here, times t. Finally, the range is r equals Vx times t, where this capital T here is the total time of the flight. The range r simply means that what displacement will the object have along the horizontal direction when it lands. So how far away does the projectile land along the x-axis? The motion along the y-axis can be described with the constant acceleration ay equals minus g. Why do we need the minus sign? Because the y-coordinate is chosen to be positive upward and gravity acts downward. The initial velocity is simply the other component of the velocity vector, so Viy equals Vi times sine theta. Remember that we took the cosine of the launch angle theta for the horizontal component, and now we take the sine. The displacement as a function of time can be given using the formula for motion with constant acceleration. So delta y equals Viy times t minus 1/2 gt squared. To get the maximum height that the projectile reaches, we have to start from one of the equations of motions that we learned previously, which is the velocity displacement relation. It states that Vy squared equals Viy squared minus 2gh. At the top of the trajectory, the y component of the velocity is 0. So substituting 0 for Vy and expressing h, we get the height corresponding to this point. Therefore, the maximum height is h max equals Viy squared over 2g. Another interesting question is the time of flight. As we saw, the y-coordinate of the object can be expressed as yt equals Viyt minus 1/2 gt squared. The flight ends if the y-coordinate becomes 0. So substituting y equals 0, this yields a quadratic equation for the time. The quadratic equation has two solutions. The first solution is t1 equals 0, which of course just corresponds to the time of the launch. The second solution is t2 equals 2Viy over g. This will correspond to the time of landing. So if we start the projectile from the ground level, y equals 0, and it ends its movement at the same level, then this is the formula to calculate the total time of the flight. So then the total time of the flight is 2Viy over g. But you have to be careful. There might be problems where we launch a projectile from a tower, for example, and then you have to change these formulas accordingly. So I would advise you not just to memorize these equations, but understand the logic behind them, and then you will be able to apply them to any problem. There are a couple of guidelines of how can you solve problems involving projectile motion. First, choose a coordinate system and resolve the initial velocity vector into its x and y components. Second, Follow the methods used for solving constant velocity problems to analyze the horizontal motion, and follow the methods for solving constant acceleration problems to analyze the vertical motion. And finally, remember that the motion in both x and y directions share the same time of flight. If you need to connect the equations corresponding to the different directions, you can use this fact. Now, let's solve the following problem. A kicked football leaves the ground at an angle theta equals 37 degrees with a velocity of 20 meters per second. Calculate the maximum height, the time of travel before the football hits the ground, the horizontal range, the velocity vector at maximum height, and the acceleration vector at maximum height. Assume the ball leaves the foot at ground level and ignore air resistance and the rotation of the ball. First, we calculate the velocity components. The x component, Vix, is Vi times cosine theta, which is 16 meters per second, and the y component, Viy, is Vi times sine theta, which is 12 meters per second. From these, we can already answer part A, which asked us about the maximum height. So Hmax is Viy squared over 2g, as we saw previously. Substituting the given data, it will be 7.39 meters. Next, part B asked about the time of flight. This will be t equals 2 Viy over g, which is 2.46 seconds. In part C, we had to calculate the horizontal range. Using the formula r equals Vix times t, we get 39.2 meters. In part D, we have to give the velocity vector at maximum height. Remember that at maximum height, Vy equals 0. And Vx, the velocity in the x direction, is unchanged for the whole movement. So from these, we can simply give the velocity at the top as 16 times I plus 0 times j, of course expressed in meter per second units. And finally, part E is about the acceleration vector at maximum height. To solve this, we have to remember that the acceleration is constant and it's equal to minus g everywhere. Thus, the answer is the acceleration at the top, or anywhere else, is 0 times I minus 9.8 times j, again given in meter per second square units. One more important topic is the range and time of flight for different launch angles. The same range can be achieved using the same initial velocity through complementary angles. So, for example, at 15 degrees and 75 degrees. But as you can see from this figure, the maximum height will not be the same. The total time will also differ between the two cases. Can you figure out which one takes more time? There are several more examples for projectile motion in the booklet. Go through them and try to solve the problems yourself to test your understanding. Thank you for your attention and good luck in the competition.